GaussianHand, real-time 3D Gaussian rendering for hand avatar animation. In this paper, we propose GaussianHand, a real-time 3D Gaussian rendering method for hand avatar animation. In the training phase, our method takes a sequence of sparse view images of the user's moving hand and its corresponding roughly estimated nano-parameters as inputs to train the GaussianHand model. In the inference phase, given nano-parameters, our GaussianHand model can generate realistic animated hand avatar with free viewpoints and free poses. In mixed reality application, based on an off-the-shelf pose estimation model, our approach is robust to arbitrarily complex user input poses beyond the distribution of the training set and can simulate the rendering of free viewpoints in real time. Compared to the state-of-the-art real-time method LiveHand, our method achieves better rendering quality. LiveHand used 139 training views, while we used only 20 training views. The rendering results of our approach are more realistic and natural, especially in terms of the clear appearance of wrinkles, nails, and blood vessels. Our method has three main steps. The first step is to estimate animatable hand Gaussians properties. We initialize unposed canonical Gaussians on the nano surface. Through the standard linear blend skinning, we can achieve the initial posed Gaussians. Our network estimates the Gaussian color, scale properties, as well as other necessary properties of our proposed modules. The second step is to use hand Gaussian blend shapes to model the non-smoothed hand surface. The geometry of canonical Gaussians are optimized by the position offsets of hand Gaussian blend shapes, which are composed of the learned Gaussian shape basis and the blend coefficients, to achieve blend-shaped Gaussians. The third step is to use linear blend skinning with neural residual skeleton to deform the blend-shaped Gaussians, and attain the final posed blend-shaped Gaussians for splatting rendering. The neural residual skeleton and the learned residual skinning weights together act as a residual term to rectify the linear blend skinning. In the qualitative evaluation experiment, we compared hand avatar and LiveHand with our method under 5 and 20 training views, alongside the ground truth images on Interhand 3.6M dataset. Our GaussianHand demonstrates the best rendering quality with only 20 views. We summarize the qualitative improvements of our GaussianHand as fourfold. Nails: hand avatar's nails lack realistic colors and shapes, and LiveHand's nails appear blurry. Our GaussianHand can render high-fidelity fingernails. Our GaussianHand under 5 views can also render nails effectively. Blood vessels: hand avatar only reconstructs the obvious veins in the lower right, ignoring the more subtle ones in the upper left. LiveHand tends to blur the thread-like vessel shapes. In contrast, GaussianHand can render the blood vessels bulging on the back of the hand. Shape consistency: hand avatar tends to reconstruct the fingers to be overly rounded, and LiveHand's fingers tend to have unnatural bumps at the knuckles. Our GaussianHand can maintain the consistency of finger shapes across different poses. Wrinkles: LiveHand's results are blurry. Our GaussianHand can render realistic wrinkles on the palm. We show more comparison results with LiveHand for varying poses and views. The animation rendering of our method is more consistent with ground truth. Our reconstructed nails have white edges, consistent with the ground truth, while LiveHand's nail color is flat and thus lacks detail. The wrinkles of our method have higher fidelity. LiveHand's results are blurry. Our method reconstructs the skin folds produced by the thumb poses, whereas LiveHand's results are overly smooth. We compared our Gaussian hand model with HARP and UHM on the hand appearance dataset. Our Gaussian hand renders hand appearances with greater fidelity than HARP and UHM. Specifically, the first row shows that our method renders the details of tendons and blood vessels on the back of the hand, whereas HARP and UHM produce blurry results. The second row illustrates that Gaussian hand effectively captures pose-dependent variations in appearance. Notably, the tendons on the back of the hand become more pronounced in a spread pose, compared to the grasp pose shown in the first row. In contrast, the tendons in HARP and UHM remain blurry, similar to those in the first row. In the third row, we observe that our method renders clear and natural wrist wrinkles, while HARP and UHM show overly concave tendons. Finally, the last row confirms that our model produces fingernails with higher fidelity than both HARP and UHM.